All right, welcome to worksheet number 25. This one will cover section 5.2 from our textbook. Here we try to find the volumes of different objects. In this section, we'll learn how to find the volume of an object. In the previous section, we learned about how to find area by subdividing region into approximating rectangles. So our strategy was we have this random area and then we just split that into a bunch of rectangles. Because we know how to find the area of each rectangle, then we'll do a bunch of stuff. For the volume, we'll have a similar strategy. We'll subdivide the solid into approximating boxes or cylinders to estimate the actual volume. So let's kind of look at so there's a box, this is a cylinder. How do I find the volume or volume of a box or a cylinder? So, okay, box, we have it's a width and then length and then height. So volume of a box is width times length times the height. When you kind of think about it, if you just get the width times the length, that gives you a rectangle, right? So this is like rectangle. So when you think about this is area of a rectangle that we have in the bottom of the box. So when you think about it, it's like, oh, isn't it just area of the rectangle times height? The answer is I can kind of look at it that way as well. Same here, I have a cylinder. Cylinder has a circular base. Like in math, generally cylinder can have any base, so I can consider this as a cylinder. I have a base here, I have a top here. So as long as a base and the top, if they have the same shape, we can call it a cylinder. I know it's kind of weird, but so here the volume is V is equal to pi r squared times h. This is r. R is for the radius. H is for the height. You can kind of notice that, oh, can we look at this part, the circle part? So this part is area of a circle at the bottom part, right? The base. So here we have area of the base times height for the box. Area of the base, which is pi r squared times height. So if I had a triangular one, triangle at the bottom, and then we have a cylinder like this, then the volume is basically area of the triangle at the bottom times the height, h. So they all have a similar structure. So we're going to utilize either is area of the base times height, area base of the times height. If area of the base is a rectangle, it's the area of the rectangle times height. If the area of the bottom is base is circle, then it's area of the circle times height. So I'm going to keep that in mind. Okay, let's see how do we actually find the volume of a solid. That has to be a solid that lies between the plane x is equal to a and x is equal to b. X represents the cross-sectional area of S. So this is kind of like what I was talking about. This is the area of the base of a cylinder, right? So this is area base of the cross-section. Cross-section is going to be like our sub-intervals. Then the volume is determined by this. So I know it looks kind of scary and kind of confusing, but if you look at this and dx, it's like, oh, okay. So dx is going to be the thickness of a cross-sectional slice. So this is going to be the height. And this is going to be the area of the bottom. Area of the base. Right? So where do they come up with this? This is area of the base times height. Height is denoted as dx. So once you take the limit as n goes to infinity, then basically it's that, right? So we're going to use this concept to find the volume of a solid. We'll look at the area of a cross-section. We'll look at the slices. That's like our sub-interval. And then dx. This is when we have cross-sectional area at each point x, right? Okay, so here is where they come up with. So I have this solid here. It looks like a potato or something. So what are they doing is they're slicing it this way, perpendicular to x-axis, right? Imagine you're slicing your potato. So you get these chunks, right? So basically, we're trying to find the area of each chunk, add them all up, that'll approximate the area of the, volume of the entire thing, like a whole potato. So how do I find, let's look at the last chunk. Like how do I find the volume of this chunk, the last one? Well, this is going to be the height. So this is kind of oriented like sideways. And this will be the area of the bottom part, right? So this will represent A of x, and this will represent delta x, right? So that will give you their volume of this chunk. Then I calculate the volume of the next chunk, so on and so forth, add them all up, and then approximate that, and then make this slice thinner and thinner, so eventually we get the exact answer. So the estimate the volume of the ith subinterval, so these are my subintervals, cross-sectional slice, so the volume is going to be the area of xi star times delta x. So ai star is representing this bottom base, the area of the base, and delta x represents the height. I chose delta x because this is difference of x values because it was going this way, right? So I want you to kind of remember, if you slice it perpendicular to x values, then the height is going to be dx, delta x. Okay. So basically we let n goes to infinity, and basically that's what the integral is. Axi star will just becomes ax, delta x becomes dx. When you sum up and then take the limit, it becomes the integral. So notice that delta x is the thickness of the disk. So like I called it chunk. It has different names. I can call it a chunk or a disk. So that's like thickness, the height of a chunk. So maybe I should write it as height also. The height of a chunk. And the integral is set respect dx. Because later on we're going to do a dy, so I'm like, we have to decide how do you know it's going to be dx and dy. So that's coming. Let's look at example 1. Find the volume of solid whose base is bounded by the semicircle disk. So 16 minus x squared. So this comes from x squared plus. So this comes from x squared plus y squared is equal to 16, right? So this is just upper half of a circle, radius 4. So there's my circle like this, semicircle. Okay. And then it says the cross section, so semicircle, and the x-axis, so this is x-axis, this is a semicircle, and cross section to the x-axis is a squares. So what does that even mean? So that means if I do get the cross section to the x-axis, so cross section is like this way, right? Then you'll see a square, so it would be like something like this. If you cut something here, then you'll see something like this, right? So I'm building like a three-dimensional thing. If I cut it here, you have a very small rectangle, right? So if you cut it here, you get the big rectangle. So you see like a shape that goes like this. So it looks kind of like, what does it look like? Observatory, where the important thing is when you this is really not a good drawing, sorry about that. If you look at the cross section, if I cut it this way, you're going to see a rectangle. If you cut it here, square. If you cut it here, you're going to see a square. So every time you cut this way, the cross section you're going to see is a square. Oh my god, it's not helping that much. So that's what we need to know. All right, so it says find the volume. So I'll kind of use the integral we looked at here. Basically, I'm going to use this to set up the integral to find the volume. So let's see how I'm going to set it up. I'm going to go integral. I know it's going to be dx because I'm cutting perpendicular to x-axis. So each one, the thickness is going to be, so for example, I'm going to use red. If I look at one slice, it's square, but you're going to have a little bit of thickness like this, right? So I'm going to think of this chunk as my approximating chunk. So dx is, delta x is like this way. So I'm going to go with dx, right? And then we have to look at the area of a cross section. Well, it's a square, so it's this times that itself square, right? So how do you determine this length? It comes from this circle, right? So height is going to be just that. It's going to come from here. So height is gonna be, the area of a square is just base times height, so it's this times that, right? It says squares, so this length is gonna be same as this length. This length comes from this graph, that's why I put this, and then because they say square, it's the same thing, right? And then your x goes from -4 to +4. I can use the fact this is like an even function, like this is symmetric. So what I can do is I can go from 0 to 4 and then times 2. So this will give you the quarter of the circle, and then this will give you the semicircle, because that's what we have. All right, so how do you actually integrate that? That's 2, 0 to 4, 16 minus x squared. Again, square root of something times square root of something is, we don't have a square anymore, the x. So let's see, this will be 2 times 16x minus 1/3 x cubed, and then 4, 0. So that's 2 times 16 times 4 minus 1/3 times 4 to the third power, 64. 2 times 64 minus 64 over 3. 64 is 6, so that's 128 over 3. So that'll be 256 over 3. All right. All right, so more of the story here was that I used the fact that I look at the area of the cross section, and I did dx because the thickness of each chunk was according to the x. Because I sliced it perpendicular to x, the thickness will become x. So delta x was like this way, so I used dx. That means everything has to be in terms of x. All right, next, this is a more general case. We'll find the volume of solid generated by a rotating region. So when you rotate something by construction, we're going to get a circular cross section. So we're going to keep that in mind. So anytime you rotate something, you'll see like a circular cross section. We'll use that fact to find the volume, right? So let's say you have like a water bottle or something like that. It looks like this, right? I can think of it as by doing something like this. You have a shape like this, right? And then you rotate it. So imagine I'm rotating it, right? So when you rotate it, you get like a shape they want, right? So I can kind of think of a water bottle as by looking at this blue area. Imagine this flat blue area. And then you just rotate about y-axis, and what it generates is like a full-on water bottle, right? So a lot of things we use in real life has that kind of shape, and you can kind of think of it as like a rotation of some sort. Okay, all right. Okay, so kind of same thing. We have a region R bounded by some function x-axis and the vertical line x is equal to a. So that kind of defines the region we have. So you have like a graph. We have x-axis and you have some boundaries here, and then we're revolving it around x-axis, right? So if you look at the picture here, I have a graph. They have the region here, region R, and then you're rotating about x-axis. So imagine like circulating this, going around this, going around the x-axis here, going around the x-axis. So by nature, you're going to get some circular cross sections, right? So here is almost like that, except now we are just orienting it different ways. So again, when you rotate about x-axis, your thickness of each chunk is going to be dx. Delta x is here. So that's why they're using dx. And then you'll see it's like pi f squared. Where do they get that? So let's kind of look at the picture and see where they come up with the pi f squared. So if you kind of look at each disk or each slice or each chunk, volume of each one, again, is delta x, right? And then we get a circle. Well, how do you get the circle? Circle has radius r here. So radius r is this length. How does it determine by? It's determined by this function, right? So if function is high, then your radius is going to be higher. If function is low, your radius is going to be smaller. So radius is determined by the function. So this cross-sectional area is going to be pi f of xi star square times delta x, right? So this gives you area of circle times delta x gives you the thickness, which is the height. And how do you know it was going to be delta x? Because we are rotating about x-axis. So I know that each slice is going to be circled if I cross it this way. That means that's going to be delta x. That's where they come up with the formula here. All right, let's look at the next one here. Look at the example 2. And let's erase this one here. It's not erased. All right, so it says example 2, consider the region bounded by curve y is equal to cube root of x. So that is y. That's your f of x. The line x is equal to 8. X is equal to 8. So 8 is probably here. I'm going to just mark it. So that line is x is equal to 8 is this line. This graph is this right here. And the x-axis, this is x-axis. So they're talking about this bounded. So I have this line, I have this line, and I have x-axis. So this region is my R. A lot of times they call it region R, so R, so I'm going to call it R. And then find the volume of solid generated by revolving the bounded region about x-axis. So imagine, just like the water bottle, imagine I'm rotating it about x-axis, right? So this part will go rotate around like this. This part will go rotate around like this. This part doesn't really have a rotation. Here it goes rotate around like this. So you're going to get something like this, right? Let's see, how does it work? So integral. First, I have to decide if it's going to be dx or dy. I mean, I know it's dx because I'm rotating about x-axis. So when I look at the slices, it's going to be perpendicular to x-axis, right? So like this is one particular disk. So that thickness is dx. It's like that much of x, right? So every time I cross-section, look at cross-section like this, it's going to be dx. So fine, dx. And it's going to be pi r squared because I see a circle because we rotated. So my cross-section is going to be a circle. Again, so I have pi. And then radius is determined by this function, right? That's going to be the radius of this circle. So I'm looking at one particular cross-section. Oh, this is circle. This is radius. So pi r squared, and which is the function. So x to the 1/3 power squared. And then x goes from 0. This is dx. So I have to look at the smallest value of x to the largest value of x. It says x is equal to 8, so it goes from 0 to 8. So I'm going to write 0 to 8. So let me rewrite this. Pi is just a constant, so I can leave it outside. It's like this. So how do I integrate that? Raise the power by 1 and divide. So that's 5 over 2, 3/5 x, 5 over 3, 8, 0. So what do I get here? 3 pi over 5 times 8/5 over 3 minus 0. Right? 1/3 power is cube root of 8 is 2. So that's 2 to the 5th power, which will be 32. So 3 pi over 5 times 32 is 96 pi over 5. Yay. All right. Let's look at the next part. Now we can kind of have a same thing. R is bounded by these two functions. So it's like a sandwich in between two functions, right? Between the vertical line this, and then f is bigger than g. So this is like the outer circle, and this is going to be the inner function. Like this is a higher function, this is lower function, right? And then you get this. Let's look at the next example and see if it makes sense. So example 3, consider the region bounded by the parabola y is equal to x squared. So this is y is equal to x squared. And then x is equal to y squared. Okay, fine. Why did they give you it that way? So that's going to be like this one. Another way to look at this is like, can I solve for y? This is weird that x is solved in terms of x. But sometimes it's actually, we need to solve for x so that we can do it according to dy. So y is equal to, but right now, this kind of looks weird. Maybe I can think of it as a y is equal to radical x because we are squaring root both sides. Find the volume of solid generated by revolving the region. So this is my region R. You can see it there, connected here. And about x-axis. So I'm going to rotate it about x-axis like this way. Later on, we're going to rotate it the other way around. Then you're going to get something very different. But here, at least we're going this way, right? So here, this point is going to rotate around x-axis. So it's like this. This point is going to be rotated about x-axis. So it'll be like that. So this will be like a smaller disk. This will be a bigger disk, right? So again, since we're orienting it like this, our cross-section is going to be a circle. In order to get that, you have to cut it this way, right? That means you're doing dx because that will be the thickness. So I'm going to set it up like dx, right? And here, they gave you that this is 1, but how do you know they meet at 1? I have to actually set them equal to each other, right? Y is equal to x squared, and then we have y is equal to radical x. So how do you technically find this point if it was not given? We just let them equal to each other. And then we can square both sides. So x4 minus x is equal to 0. That means x cubed minus 1 is equal to 0. So x is equal to 0 and x is equal to 1. Okay, because then x is 1, 1 cubed minus 1 is 0. So that's, we know it's going to be, so I'm going to go 0 to 1. They meet 0, they meet 1. So all the x values, so I'm doing dx. So this is smallest x value, this is largest x value. If you look at our disk, there's a hole inside, right? Like for example, like I'm going to put another one. If I look at this particular disk, it's like, it's empty inside, right? So it's like a CD. I don't know if you guys know a CD or DVD or Blu-ray. So it's like this. So how do you find the surface area of this thing? Well, it's the bigger circle minus the smaller circle, right? Because it's not including, the inside is empty. So I'm looking at this, so this part is going around, right? So this inside is empty. So the surface area of this cross section is just, that's where they come up with the formula. So pi, the bigger circle, which is this one, because that's the bigger circle, which is this function, is radical x. So radical x squared minus pi small x, which is x squared dx. You can obviously factor out pi 0 to 1, radical x squared plus minus x square. So pi 0 to 1, x minus x to the 4th dx. This is how I'll set up. And if you finish this, you get 3 pi over 10 as an answer. All right, so this section is pretty long, so I'm going to end here as a part 1, and then I'll upload a separate video for part 2. I'll finish the rest of the worksheet.